Good afternoon, everyone. It's amazing to be at Elixir Conf. This is my first time being at Elixir Conf. I have my friend on the line. Ridwan, do you want to say hi to the room?
Hello. Hi.
Hi, Ridwan.
I was present last year in person, but I couldn't make it this year.
All right, cool. A little bit of an introduction. Who are we? Like she said, my name is Pelumi. I currently work as a vice president software engineering at Bank of America in Dublin, Ireland. Most of the time, I am writing Python or I am writing Elixir. And when forced to, I do write JavaScript. Ridwan?
Yeah, I'm Ridwan, VP of Engineering and Product at JCWay. I spend most of my time writing Elixir, but I used to write Ruby and I've recently been writing Zig also. I live in London. Yeah.
Okay. Give me a second. Sorry about that. Okay, yeah. In case you haven't guessed, we're both from Nigeria. We've been working on building an AI observability tool called MonitorLizard, and working on that particular product, some of the learning, some of the challenges we faced is one of the reasons why we've actually built out this framework, which we're calling Whisperer. So, if you're like me, across the last 2 years, right, you're probably frustrated with all of the buzzwords that's been coming out of the AI space, and you're thinking, what exactly are agents, right? If you're an Elixir developer, you only know one type of agents, right? And I'm sure we're all familiar with this. An agent, a process that encapsulates state, right? And then circa late 2023, early 2024, all of this branding regarding agents has come to be. And the question is, don't we have that already? Not really. AI agents is a slightly different paradigm, still building on one of the core principles that we have in Elixir, which is state management, but with some additional tooling, right? And so, some of the buzzwords, right? And so, alongside this new introduction, we get a bunch of other buzzwords, right? And it's this massive craze going on, right? You're hearing stuff like agentic workflow, agentic, LLMs, tool calls, MCP servers, multi-agents, right? How does any of this actually translate to any sort of engineering excellence and, in the long term, business value, right? Should an AI agent be fully autonomous? Is that what it is? Should it utilize various tools? Should it have predefined workflows, right? From the work we've done at MonitorLizard and experimenting with this new paradigm, we believe that a proper AI agent or agentic system should have all of this. And so we like to define AI agents as consisting of LLM building blocks. So if you've changed some underpinning model to your agent, then it's an AI agent. If you've provided the functionality to be able to do RAG, right? Do some enhanced retrieval, or if it has some tooling, or if it has, they'll call it memory now, right? We've always known it to be state. They'll call it memory. Or if it has the ability to interact with MCP servers, then that's an AI agent.
Yeah. So it's not enough, right, that you have agents that can call LLMs to do specific tasks, right? Sometimes you have complex tasks, that needs to be done and requires like multi-step agent calls and stuff like that. And the best way to handle those kind of cases would be, some sort of workflow where you have multiple steps or multiple jobs or tasks that need to be done, and each task is executed. It could be executed sequentially, it could be executed in parallel, right? But the most important thing is you can literally chain multiple agents, multiple tasks to achieve a more complex task, right? And we've noticed that, there's some patterns, some recurring patterns when working with, workflows. especially agentic workflows. There are sequential patterns and there are parallel patterns, right? For the sequential patterns, it usually involves the route, like the tasks or jobs or routines, whatever you may want to call them, or the individual agents that call the LLMs, right? And each agent or each routine in the workflow is executed one after the other with inputs going into the first one, doing the task, then handing off the output from that first task to the next task within the workflow. So it goes sequentially one after the other, right? Then we have the parallel workflow where you'd want to execute these agents concurrently or at the same time, right? Because maybe the output from one of the agents is not really required for the second agent. Or, for example, let's say you're trying to do some research and you want like multiple opinions. So let's say you're trying to run an analysis, but you want to run it with three different large language models. You can pass the same input, then execute those three in parallel, then aggregates the results to get a final output that that has high confidence value. So breaking down the sequential workflow patterns, we've classified it into two major buckets: the classifier router workflow, which involves getting an input, classifying that input to know what type of task do we need to what type of task are we trying to perform, what are we trying to achieve, right? And then routing it to the appropriate agents within the workflow that can actually tackle that specific task. So say you get a request, a customer support query, right? And the prompt is they'd like to initiate a refund. Yeah. The classifier classifies that input to know, okay, this input is about requesting for a refund. That means I need to pass the LLM call to the agents that would undo refunds. So instead of going through every single agent within the workflow, it's just going to route it to the refund request agent, and you get your result. And if you need maybe additional technical support after you've requested for that refund, right? It takes the output from the step for requesting the refund and passes it to the technical support agent to continue, processing that task. So that's typically how the classifier router workflow works. Then the other one is the sequencer orchestrator workflow, or what I typically like to call like the cascading workflow, right? So there is a central LLM, right, that breaks down this task. So assuming there's a complex task that you'd like to do, let's say deep research, right? This deep research typically involves gathering information, analyzing the information, then probably generating a summary, right? So you would have this central LLM, which is the orchestrator or the sequencer, that breaks down this complex task of doing a deep research into those subtasks, right? Then so it breaks it down and also specifies the order at which those tasks need to be run. So the first one is gathering the information. So you hand off to the agents that gathers the information from the web and stuff, right? That gets the result and hands it off as input to the next agent, which analyzes the information, gets the result, and hands it off to the final agent, which would, generate a summary. So it's more like an orchestrator that works based on predefined sequences of, tasks and agents that need to be run. Then we have the parallel workflow. These are this is a workflow where the agents or the individual routines or tasks are executed simultaneously on a specific input, right? So the input flows in. It's more like a fan out mechanism. One input flows in, then it fans out to different agents that act on the input, produce different outputs, which is then aggregated by an aggregator to give a single output with high confidence value. This workflow pattern is usually employed when speed is important and when the output is not dependent on previous input from previous agents or routines within the pipeline. Typically, in production systems, you definitely be combining these patterns, and the success within the LLM or agentic space isn't just about building, the most sophisticated system that you can build. It's about piecing together the pieces that you need to get the optimal results that you want. So you probably start with simple prompts, optimize them, with comprehensive evaluation. If you need multi-step agentic workflow, you start adding agents to the start adding steps to the workflow to generate or achieve specific tasks that you need when, the simpler solutions fall short.
Okay. So what are some of the popular existing agent frameworks in the world? If you're familiar with the Python ecosystem, I think LangChain was one of the pioneering frameworks who tried to look past, just an LLM model and try to think about how can we sort of keep track of, what responses we've received from the LLM. How can we provide a generalized set of APIs to, interact with this LLM, right? And LangChain has gone on to inspire, so many frameworks, so many ideologies within the AI space. But it was immediately inherent that, there were certain issues, right, with working with LangChain. The biggest one is LangChain has no first-class support for, working with multiple agents. So if you're really trying to force it to work, you could, in quotes, have multiple instances of, this LangChain, but they are not really aware of each other. How do you actually, sequence work between them? And for anyone that has spent some time working in Python, you know that working with states in Python is not exactly the best thing, right? So I feel like we're a bit, spoiled in Elixir. State is trivial for us, right? Encapsulated state is trivial for us. But I can't even begin to think about how I would write proper Pythonic code that would have different encapsulated states for each agent, right? And have all of those, all of those existing autonomously, simultaneously. As I'm saying all of this, I think it's really obvious which language, does all of those things trivially, right? So LangChain had all of those limitations, and I think sometime in mid-2023 or early 2024, LangGraph was born out of that work. And LangGraph sought or seeks to remediate some of the limitations that we've seen with LangChain. Most importantly, the biggest limitation, it provides an approach for actually defining individual agents or individual encapsulation of work or individual encapsulation of states, and a methodology for having all of this interact with each other, be aware of each other, and basically share information. Like we will see with most of these systems, right? There isn't exactly something really new, right? Because they didn't come up with a new data structure. They didn't invent anything new. They used some of the existing battle-tested principles that we are familiar with as computer scientists, and they used the graph, right? The graph data structure underpins LangGraph, as the name would suggest. So those that's an analysis of two of the more popular frameworks. I focused especially on Python because that's something I'm quite familiar with and something I also work with. And so coming from this, why would I think that Elixir, makes a better language to be able to actually build out agents as well as a multi-agent framework? Like I said, states is trivial to us using the actor model. Each of these agents can be a single process, and we even get the added benefits of even having a supervisor, such that if things happen in production, right? If we, for any reason, lose that particular process, the supervisor can start it up. So we have guaranteed resiliency of our agents, something that would involve so much work to establish in other languages or other stacks, right? And as these AI systems begin to get popular, I think anyone that works with Copilot or Cursor or Windsurf knows that a lot of times what the issues you face are actually bad responses, right? So you're trying to work with Windsurf or you're trying to work with Cursor, and a lot of the times the queries you're sending, depending on the tier you're paying for, a lot of the queries you're sending are coming back, erroring out or connection refused or whatever, right? Because we can tell that these are highly computationally intensive processes, right? And their SRE/production team are literally fighting fires, trying to get the systems to be able to scale and handle the amount of requests that us users are making. In an Elixir world, this becomes trivial, right? Because we can spin up multiple processes, spin up multiple agents, and so scale for us, is trivial. It's really the magic of the beam. So we know why we should use Elixir for this, right? But what are some of the things that we want to see from a multi-agent framework? If you've been working in the AI and LLM space, every time you're working with a particular tooling, right, it always feels like the APIs are usually an afterthought, right? It doesn't feel intuitive. You're asking yourself, why exactly is this object built this way? Or why exactly has this function been designed this way? And so something that I personally set out to build from the start was interfaces that felt natural, interfaces that I felt like would mimic how we think about multi-agent systems and interacting with agentic workflows, right? Also, we wanted to have a proper modality for being able to hand off actions across agents. So, if we've determined that agent A is next in line to execute some particular work, how do we actually go about handing off the result from agent A or B, which was upstream of that agent, give it to it, collect results from it, and give it to another agent, which is downstream of that particular agent in the entire sequence of work. Something that we also thought about was making the agents agnostic of LLM technology. Now, why is this important? With machine learning and AI, it's always waves, right? About 5 years ago, I think we were having the CNN, KNN, RNN waves. Today, it's LLMs, right? And we didn't want to build something that would be intrinsically tied to the idea of LLMs. We wanted something such that, if the idea of executing intelligence changes in the next 5 years, whatever we've built today should still be plug and play for however that mechanism might work. I don't know what that will look like in 5 years, but however it is, we wanted something that, this sort of framework can still be relevant in those 5 years, not necessarily thrown out the window or having to reinvent, the wheel again. And something that was scalable, a framework that will, be able to scale with increasing workloads, something that is reproducible. Now, why reproducibility was important for us is working with multiple agents in production systems, we sometimes found it quite difficult to be able to tell what exactly has been the route that has been taken to be able to get this particular output from this set of agents. So we wanted to be able to, given a particular output, wanted to be able to tell that, okay, this is the agent that ran this first, went to this, gathered these two outputs, aggregated it, and provided it as an input into this, third agent. We wanted to be able to, retrieve the entire process, right? Because we know that, sometimes when working with these production systems, you want to have an idea or an insight into how you've gotten this particular output. And then a framework that is reliable. For us, Elixir gave us reliability and scalability trivially. We didn't have to do anything fancy or new to achieve that.
Yeah, so today we're introducing Whisper, which is an Elixir-based flexible agentic framework. That sounds like a lot of buzzwords, but it's basically our take at implementing some set of behaviors, right, that we think agents should implement, and how those behaviors should be composable into like the workflow pattern, right? Um, Today, Whisper works based on the sequencer orchestrator workflow pattern that we've described earlier. It assumes that you've implemented a sequencer and you pass that sequencer to us when initializing the workflow. So we know how to go about executing the agents within the workflow engine, within the pipeline. So how does Whisperer work? We have a central orchestrator, right? And we've implemented these as gen servers, processes that are supervised and stuff, right? So that when anything breaks or when something happens, we can easily restore the system to a good state by through our good old supervision techniques, right? So we receive let's say we start, an orchestration, a workflow, or start a stream of work, right? We'll pass it an input and also the sequencer, right? What happens is a process is created, right? Which basically sets up our whole workflow engine for this agentic system. Then we can decide to add agents to that workflow, similar to how you would add what's it called? How you would add jobs or tasks to like a workhouse, something like that. So you can add your agents to the initialized workflow, right? And when you're done adding the agents that you want to add, you can start the execution. And what happens at execution is the sequencer that you've passed, which is a module that implements some behaviors, right, is called to determine the sequence in which the agents should be run to achieve the result. So your sequencer could be an agent itself. Your sequencer could make use of an LLM to sequence tasks based on one, the available agents that you have, two, the input or the prompt from the user, right? All you have to do is just pass the sequencer, and the sequencer should implement a specific behavior that we've defined. So when we call it, it does all the background work that you need to do. So after sequencing, right, our orchestrator then takes that sequence of agents or tasks and goes through each task one after the other in a sequential workflow to achieve the final, states that you want for the computation or question or anything that you're trying to achieve with this pattern. So this is how our orchestrator works, which is it's like the brain box of this our agents workflow. It's a gen server that manages the delegation of work to the agents, and it's implemented as when the sequencer generates the sequence, it generates it in form of some sort of graph, right? An acyclic graph, right? And we use some techniques like breadth first search to, go through that graph to determine how we're going to run or delegate the work to these individual agents within the graph.
Okay. So what does the interface for Whisperer look like today? If you wanted to get started with Whisperer today, the first thing you have to do is define your sequencer. This can be something as simple as, say, giving 3 agents, always executes from agent A to agent B to agent C. Or it can be something, in quotes, as complex as what you see in the wild, where you just delegate that to an LLM. So you say, oh, LLM, given this particular input, these are the agents that exist, creates a sequence that you think, should be used to determine the solution to this input based on the agents that have informed you exist, right? That's what most people will typically do. Once you have that sequencer, you initialize your session or your orchestrator for that particular multi-agent workflow. You pass in your sequencer, and then you also had your agents, right? Your agents are also processes that the orchestrator can reach out to execute some particular task. And then you begin to evaluate your inputs, right? So you pass your inputs or your prompts to the multi-agent system, and you get your responses, right? A little bit about how the code looks like. I'm not sure if this is, yeah. So you can see that I have a sequencer defined. That is multi-agent.sequencer. This is really not the greatest background. Sorry about that. I pass it to start the MES system, the multi-agent system. So that is whisperer.start session. I just created a session ID, a unique reference to be able to basically keep track and access that particular MES system. And then once it's initialized, I basically had agents which I've created, and then I begin to process inputs. So today for the actual demo, what we've done is we've taken one of the classic mathematical problems to be able to show this framework in action. So BODMAS. And if you remember BODMAS, I hope that's a mnemonym that you people are familiar with as well. So BODMAS, like to be able to solve a simple mathematical expression, bracket of division, multiplication, addition. Everyone knows what I'm talking about, right? You do? Oh, so I guess that was something peculiar to our own education. So BODMAS is a mnemonic, right, for solving mathematical expressions. So given that you have something like bracket 2 plus 2, bracket close, times 5, BODMAS says you solve the brackets first, then you do the off statements, then you solve divisions, then multiplications, then addition, then subtraction. So as you'd imagine, that flow is perfect for a multi-agent system where solving the brackets is a specific agent, solving the addition, a specific agent, and so on and so forth, right? And so what we've done, talk is cheap, let me show you the code, is we have this Elixir live book. So as you can see, what I have here is defining the sequencer. One major attribute of the sequencer is connections. And this connections basically builds a graph, right? In this case, for BODMAS, I have a simple graph that says, after you do brackets, you do division, then you do multiplication, then you do addition, then you do subtraction. That's a graph data structure that our orchestrator would be able to interpret and use it to execute that particular, sequence of work. I have also created agents. Agents have 2 major attributes. I think I'm using a Pythonic expression. Characteristics and process message. So characteristics is basically required for the LLMs to be able to tell what this agent is, right? So that it can be able to determine, should this agent do a particular piece of work or not, right? So you can see, for example, I have provided some details for the characteristics of the addition agent, where I've given it an agent ID, you're an addition agent, specializes in adding numbers. LLMs love those sort of details, right? And then the actual work gets done in what we call process message, right? So the orchestrator sort of uses message passing in between different agents. And so this particular agent will receive a message input that the orchestrator has created for it, and then it's going to process that message, which is where it does the work. Now, for this demo, what we've done is we have 2 sets of agents for each of these operations. For addition, we have tried to create basically a calculator in Elixir. So I have some, I won't say complex, but it might not actually be complex, some Elixir code, right, that's basically giving a mathematical expression can, compute addition, compute subtraction, whatever, right? So this is basically first principles, right? Because we trust first principles. We don't trust LLM agents. And so I'm just going to scroll down, right? So these are the simple first principle implementations. And then we have the LLM implementations, right? So if you can see this, I've created this massive prompt where I'm begging the LLM to behave properly. I've told it that, given a particular input, you're an addition agent. If you have an expression like this is what I expect. I'm basically trying to coerce it. And then, I've done the same thing for, brackets, division, multiplication, subtraction, and all of that, right? Okay, so now back to having a simple interface, right? Which was a big goal of ours. So given all that we've defined, how do we use it? Like I said, we have the sequencer. We start the session on line 8. We had the agents, and we begin to process inputs. That's for the simple BODMAS, first principles. And then for the LLM-backed BODMAS, so what we've done is we are using Llama 3 on Grok. Probably should have shown that, right? So this is it. Yes, it's here. So for the LLM agents, they are backed by Llama 3, which we are executing on Grok. So we've configured our API keys and all of that. And if I execute this, so that's basically just run through the entire graph. And that was super quick, right? Because it's first principles, no need to reach across the network or anything along the slides. The result, I can see here, in truth, is actually wrong. The answer is not 0.8. It's wrong because, I tried to implement a calculator, right, from first principles, and I'm sure I must have missed one or two things, right? But that's how it's working, without having to actually use an LLM, which was also a goal of ours, right? So if tomorrow how work gets done is not an LLM, you can easily switch out the LLM components and still have a multi-agent system. And then using the LLM, if I run this is going to take a bit of time. Network calls. Yeah. So regardless of how much I coerced and begged the LLMs, it still gave me so much results, right? They like talking. It says, I think there's been a mistake. I'm a subtraction agent, but there's no subtraction in the expression. Fair enough. It looks like I've been called to the wrong task. However, I can still help by passing the task to the correct agent. In this case, it looks like a multiplication and division task. So I will let the relevant agent handle it. The correct answer will be 3.2, right? So this sort of gives you an idea of how it behaves. And in this case, ideally, this has basically given the hands up and said, I'm not doing this anymore, right? But ideally, we should have the multiplication agents and division agents pick up that particular task, right? So this is just a quick demo that we put together. Next slide. Oh, let me go back to the slides.
Yeah, thanks for that presentation. So, although we've implemented, the framework in such a way that it's composable, plug and play and stuff, right? There's still, work ahead of us, right? For example, today we've only implemented the sequencer orchestrator pattern. Would like to implement the other patterns like the router-based pattern, parallel workflow pattern. Just implement more patterns. Also, would like to extend Whisperer to be able to act as a durable execution engine for both agentic and non-agentic system. So, for example, right now, let's say something happens and the disk crashes or there was a network failure, it's not going to pick it up from where the failure is or from. It's just going to restart everything, or you'd have to make network requests again or call the framework to process the task. But if it's implemented as a durable execution engine, we can always pick it up where we left off and continue running the process. So implementing a durable execution engine is going to be useful, for example, for long-running tasks and tasks that have a huge chance of failure, maybe because external APIs are involved and stuff like that. So that's our future plan for Whisperer over the next couple months.
That's it, everyone. Thank you so much.
Thank you very much. I'm checking the questions. And there is one that is quite long, so I'm going to read it. And then I'm going to give you the phone to read it as well.
Let's do it.
If we're running multiple agents, is there anything in Whisper to systematically deal with provider rate limits? Let's say we have 10K processes doing OpenAI calls, but we're under 1K per minute rate limit. The rate-limited requests will count against the quota, so if we don't coordinate between processes, it might take a very long time to recover if we do exponential back off.
No, fully get that. Right now, there's nothing in Whisper to account for that. I could say, try to get your rate limits up at OpenAI, but I know that comes with so much costs. I think there might be a future to have, like you said, some sort of exponential backup strategy. But frankly, it's not really something we've thought about because in our usage, we have not yet just bumped across limits, number one. Number two, I suspect that anyone that is probably doing as much skill to bump against those limits can possibly run their own LLMs, host their own LLMs, right? Which is something that we've actually been looking into as we begin to, have a little bit more usage of MonitorLizard. We're beginning to speak to providers that can give us GPUs to actually use our LLMs. So, short answer, no, we haven't thought about it, but that's a good idea. Thank you. Sorry about that was. Any other questions? I think we have.
Yeah, do we have any more questions in the room, for example? There's one.
That's it.
Thank you for the talk. I couldn't see the code very well from here. No, that's okay. Does every agent have a agent server, or how do you manage the state of each one?
That's a good one, right? Right now, each agent is not running as a gen server. Rather, what we are using is we're using the orchestrator to manage state and basically give that state to the agents, right? But I think one of the things that we are considering long-term is actually having those agents exist by themselves. And so they can keep track of their own states and just receive execution instruction from the orchestrator. Yeah, nice catch.
Yeah, but in addition to that, we also still need to maintain a central state so we can pass that state to agents within the pipeline because, different agents within the pipeline would require output from other agents, right? Depending on the kind of pattern you're trying to implement. So in addition to each agent holding its own state, there has to be a way to pass the states from those individual agents downstream when required. So that's something we're also considering.
Orchestrator states will not go away, but specific self-managed agent states can come in.